getting sound. That's good. Okay. So if we go to our data booklet and we look up iodide, there is a copper here, but this is copper 1. Whereas what we have in the question is CuI2. Each iodide is -1. So the copper has to be copper 2+. All right, and so copper 2+ would be up in the all others, which would make it soluble, which would make it aqueous, okay? I also wanted to point out that for whatever reason, we are missing on here, we've got silver, lead, and copper 1. We should also have mercury, Hg2 and Hg2+. If you wouldn't mind adding that onto your pink sheet on page 4. So you should have Ag+, Pb2+, Cu+, and then we should add in Hg2 2+ and Hg 2+. So that is mercury 1 and mercury 2.
Wait, mercury 2 and mercury 2?
Yeah, mercury 1 and mercury 2. I'll explain that in a moment after you've got it written down. Okay, so that is in your chlorides. Okay. Both the charges are 2, but they're not. Because what does this one have that this one does not? It's got a little 2 at the bottom, which means that what we actually have is an Hg bonded to a second Hg. This is this one here. And each of them have a +1 charge, which gives the overall thing a +2 charge, but it is still just mercury 1 because each mercury has a +1 charge. Mercury is a weird little dude. Like, I don't know what his deal is. He's liquid at room temperature. It's the only polyatomic metal ion. It's just weird. Okay? Yeah, what can you do? All right, be aware of it, but don't get freaked out by it. Treat it like any other polyatomic ion, okay? And if you get confused, ask. All righty? Anything else from the homework? Oh, yeah, when you are looking at copper, copper is the one you need to watch out for. There's no others like that that are there to kind of trick you. That one is there to kind of trick you. So I always think if I'm driving down the road and I'm driving too fast, I need to watch out for the coppers, right? So we need to watch out for the coppers when we're dealing with chloride, iodide, and bromide, okay? Okay. So if we are done with that, we did pages 1 and 2 here. And we had at the bottom of page 2 in our green book, unit 1, so at the bottom of page 2 in our green book, we are given this equation here. All right, and then you are given the complete ionic equation, and it just stresses that you need to take into account both the subscript and the coefficient for each of them. So this 2 has to go both here, and this 2 has to go here. But you guys practiced that, and hopefully that went well. By the way, when you practice things, if you find that you're like, I only want to do every other question because I don't have time to do every single question, that's fine. Okay, do what you need to do to make your life workable. I know that chemistry is not your only class, so do enough that you feel secure in what you're doing, okay? All right. And then on our next page, on page 3, we cancel out our spectator ions. The chlorides don't change from side to side. And so our net ionic equation then looks like this. So we can only use these 4 things, 1, 2, 3, 4, to measure the rate of reaction. We cannot use chloride. Okay, chloride cannot get used because it does not change from side to side. So let's write 4 possible equations to express the rate of the above reaction. Have you written a rate expression before? I can't remember whether you did it in Hebden.
You think the rate equals the change in amount?
It's the change in amount
Over change of time.
over the change in time. All right, so we could have rate is equal to, now if we wanted to look at number 1, we have a solid here. What could we measure about a solid?
Changes in mass of energy.
Yeah, if we have a solid, we could measure its mass. We could measure the mass at the beginning. We could have the reaction go for 10 seconds, take out the magnesium, wash it off so it stops reacting, and then weigh it again and see what its mass is after 10 seconds. So we could do a change in the mass of mg over a change in time. You should always write what you're solving for. I know it's a pain, but do it. Otherwise, I'll take marks off. What if we wanted to look at hydrogen, H+? What could we measure about that? It is aqueous. So that means that it is present in our beaker. Here's our water. And we have H+, 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 and over time, what's going to happen is those hydrogen ions are going to get used up. Is the volume changing? No. Okay, so we cannot do volume for that. Yes?
Concentration of molar.
You could do concentration. Anytime you have something aqueous, you can do concentration. So concentration is good for aqueous, solids is good for mass. All right, so we could say rate is equal to, yeah. Do you guys know how to write concentration of H+? Do you remember that from last year? What do you use? You use square brackets. My pen sometimes does weird things where it makes little jig-jags, so just ignore that when that happens. The square brackets mean concentration in moles per liter. What is another way of writing moles per liter? There's another unit that we can do that takes that and simplifies it a little bit. Yes? Big M. Okay, so another way of writing that is capital M. And does anyone remember how we pronounce that? Molar. So if I was to say my concentration of hydrogen is 1, it would be 1.0 moles per liter, or 1.0 molar. Thank you so much. Okay, so we can say we want to measure a change in the concentration of H+ over a change in time. So that deals with our solid That deals with our aqueous. Next, we have a gas. We could do volume, absolutely. For a gas, you can do volume. Okay, so rate could be a change in volume of H2 over change in time. Okay, and that's a gas. So volume works well for gas. Anyone know anything else that gases do other than have volume? Gases have volume. They also have...
No, something about like
They do have mass. Ooh, you could do mass. We'll look at that one in a moment.
That is that could be concentration, like percentage.
I know I did not teach my classes, but I know Mr. Weinberg sometimes does. So if you were in Mr. Weinberg's class, you may have done this in grade 11. Starts with P. Pressure. Yes? One of my students. I didn't teach him that. He just knew that. Good for you. Okay, so you could also do, if you have a gas, you could do rate is equal to a change in pressure over a change in time. And that's because we can use that because we make a gas. How do you measure the pressure? Basically, what you do is you have to have a closed system where the gas does not just escape. It has to be closed, and then you put a pressure gauge on it, so it will actually like measure like how much push there is on the container.
No, how do we like do it on paper?
How do you do it on paper? Oh, delta P, like capital P?
No, like will we be given the pressure if we do write the pressure, or do we have to?
Yeah, okay, so chances are you're not going to be given questions about pressure because Chemistry 12 does not worry about pressure. So you won't be given atmospheres or kilopascals or things like that. You just need to know that if we have a gas, we could measure the pressure to measure the rate. Okay? You could, as Coco was saying, you could measure the mass because the gas, if we don't have a closed system, if we let the gas leave the container, what's going to happen to the mass? If this is my container and the gas is leaving the container, what has happened to the mass? The mass has gotten smaller because a gas is produced and leaves the container. So we could do a change in mass of, we're going to say the mass of the system. The system is everything, okay? And we can do this because we have a gas that escapes taking mass with it. Taking mass with it, mass. So actually for gases, you have a lot of choices. You could measure the volume of the gas. You could contain that gas. We'll look at how you might do that in a little bit. You can measure the pressure of the gas if it is a closed system. You can measure the mass of the system if it's an open system. All right, we'll talk more about closed and open systems when we do that, but there's lots of options when you have a gas. And finally, we also have Mg2+. What could we measure about that one? We could measure concentration of Mg2+. So we could say rate is equal to a change in the concentration of Mg2+ over a change in time. And the time unit could be seconds, minutes, hours, doesn't matter. Okay? It just depends on how fast the reaction is. You would use something reasonable for it. Just so you know, concentration is often difficult to measure. Okay? Like you're like, okay, in my beaker, I start with no magnesium, and over time, magnesium appears. Yes, time is passing, magnesium is appearing, but magnesium is not a colored ion. So what does this beaker look like? It just looks like water. So you're like, wow, look at that water. And now look at that water with magnesium in it that looks just like the water without magnesium in it. So it is hard to tell for some things. Other things are easier, like hydrogen is easier because we have something called a pH meter. Have you guys heard of pH?
Oh, yeah, like the...
And it measures the acidity. And so if you have hydrogen or if you have hydroxide, if you have acid or base, you can measure the hydrogen concentration or hydroxide concentration using a pH meter, which makes it really easy. You just stick the pH meter in and it gives you a reading and you're like, oh, that was easy. Okay, we'll talk more about those when we get more into it. But you could say a choice could be change of magnesium 2+ concentration over change in time. It's just you probably wouldn't do it in real life because it's not practical. Okay? All right. So it gives you all the answers here. Let's just take a look at a few little details in here. You might measure the time to completely consume the magnesium. And do you guys know how to find change in? Change in means the final mass. Yeah, final mass minus the initial mass. And if you choose for your magnesium to be completely consumed, you will get a final mass of 0. And this would end up being a negative value. I think I mentioned yesterday that I don't mind whether you make the value at the end negative or positive. Just don't make it negative if it was supposed to be positive. You can just call every reaction rate positive, or if you feel comfortable doing it, anytime you're looking at products being formed, that's going to be a positive value. Anytime you're looking at reactants being consumed, that's going to be a negative value. So products formed gives us a positive rate. Reactants consumed gives us a negative rate. But if you make your rates all positive, I will not get mad at you. Okay? And we have a little picture here of a pH meter, okay, because hydrogen can be measured as pH. So you can find the change in pH over the change in time, and literally it looks like this. You've got yourself a little beaker, okay? You got a beaker down here, and you have a little probe that gets placed into the solution, and it gives you a readout. This one is 7.07 is the pH, which would mean it has a concentration of hydrogen approximately equal to 1 times 10 to the negative 7 molar. And we'll learn how to do that calculation in unit 4, but not right now. Okay, but you can convert back and forth between pH and hydrogen. All right? So how would we measure the volume of a gas? One thing that you can do is you can have your reaction vessel here. Okay, so in here we have some dilute acid plus magnesium ribbon. So this would be like the reaction that we had earlier where we had HCl plus Mg goes to H2 plus Mg Cl2 aqueous. And as time goes on, we get bubbles. And we attach it, usually we put some piping in there. Okay, and I'm actually going to go and get one of these measuring cylinders so you can see what it looks like. Okay, so that can be a measuring cylinder. If you don't have one of these on hand, though, you could, in theory, just use a graduated cylinder, right? Turn it upside down. Okay, and what happens is that you would fill this up and get a beaker. All right, and we fill this one up.
Maybe you should be. Oh, yeah. That's it?
I don't think I've balanced that yet, so probably needs balancing. Anywho, you would just put it like that. Now this is completely full with water, yes? And then you would, with your thumb over it so no gas gets in, you would put it in there and then you feed a tube up and into there. And then any bubbles that form, they go bloop, 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 bloop. And then the water comes out and just ends up in the beaker. And you can watch the volume over time. So this is actually a really nice way because, you know, at 5 seconds you can take a measurement, at 10 seconds you can take a measurement, et cetera, et cetera, et cetera. Okay, so that is how that method works. This is called a gas collection tube. If you're interested in the real word for it, it's called a eudiometer, but I don't know that anybody cares. So we'll just call it a gas collection tube. And sometimes instead of a beaker, there will actually be a trough. That's pronounced trough. It's one of those O-U-G-H words in English that they all end in O-U-G-H and they all are pronounced differently, right? We got though and cough and bow and oh my gosh. Anyway, this one's trough, and a trough comes from the word from, you know, those things that horses drink from? Like there's a, you know, a wooden thing and it's long and the horses go up and they drink from it. That's called a trough. Okay, so this is a trough. So it would be wider, which would allow you to you put your hand in it a little bit easier. It gives you more maneuvering room. And often there will be a little outlet on the side so that as the water comes out and comes in here, rather than overflowing the top, you would maybe have a little hose that then goes into your sink, right? So it doesn't make a mess all over the place, which is quite nice. You don't really need to know that, but just from a practical standpoint, that's why water doesn't go everywhere. You could also have a syringe, okay? So yes, just like the syringe that, you know, you would get a you know, if you're getting a vaccination, it would just be like that, except that usually these are a lot bigger. Okay, if you saw one of these at a vaccination, you would be terrified. All right, you'd be like, oh, it's so big. Okay, and in this case, it is just the pressure of the gas. The gas pushes on the syringe and this part will move out and you can measure as it moves out. Yes? And the word bung, that is the British word for stopper. So if you're like, what's a bung? That's the British word for stopper, I believe. And if anybody is British and would like to correct me on that, please feel free. But I believe that is why that is labeled as it is, stopper. And you'll notice that this stopper has a hole in it through which a glass tube goes, so you can actually have the gas come out. Okay, and then our last one, you'll note, you remember I said sometimes concentration is hard to do? You might be able to perform a titration at the end of a reaction, but if you want to measure mg, I would really choose the mass of the solid rather than mg, because doing a titration, how easy is it to do a titration? Do you guys remember doing it last year? It's a little complicated, yes? Especially when you could just be like, I'm just going to stick this thing onto a balance and watch the mass change, or measure the mass of the solid magnesium. Okay. Here we have where this is a way that we could look at the mass of the H2 over time. And what we would do is we would literally just put our reaction vessel on top of a balance. And this is our Mg, and this is our HCl. And as time goes on, the hydrogen gas will escape and the mass will decrease. Because a gas can easily pass through, you know, a cotton ball, but if there's any liquid that spatters because, you know, it's making bubbles or whatever, the liquid won't escape. So that won't change the mass of anything else. How are you guys with unit conversions?
Yay.
Yay? Okay, you should be yay by this point. So I'm actually not going to spend any time doing this. You can feel free to look at it. Okay, there are several examples here where we go from moles per minute to moles per second. If you find that these examples are confusing for you, please come in for flex time. I will bring up significant figures here just because, you know, they do come up from time to time. How many sig figs in this number here?
Wait, 1, 2, 4. No, 3 or 4, I forgot. Because it has a decimal. 2.
Okay, I'm going to give you guys 3 choices. I'm going to give you a choice of 1. Actually, I'll give you 4 choices. 1, 2, 3, or 4. So you get to choose 1, 2, 3, or 4. And have a little chat with your neighbor. And then once you think you know, you're going to raise the number of fingers that you think there are sig figs.
Everything is a sig fig. If I remember correctly.
Yeah, just don't do the.
It's lower. It's lower. Is that no. Yeah. No, it has to, it's either 3 or 4. So I think it's you know, it is the decimal. Everything is a sig fig.
Yeah, it is 2. So if you didn't understand that, let's talk it through. Zeros on the left are placeholders. These are placeholder zeros.
But I have the decimal.
Hold on. Shh. Placeholder zeros are never significant. Those are zeros on the left. And if you're like, oh my gosh, am I going to need to know these? Is Miss Spence going to care about sig figs? Yes, I am, because do they care about sig figs at university? Yes, they do. Okay, so we're going to get you good at them if you weren't before. So zeros on the left never count. Zeros on the right only if there is a decimal. So if there's a decimal present. And you can actually think about this. If you were to write this number in scientific notation, you would write it as, would you write it as 0, 0, 2.0 times 10 to the negative 2? No, you would just write it as 2.0 times 10 to the negative 2. Okay, so that is telling you that these two are not significant. If you have trouble remembering it, I like to use the mnemonic NIM, no, yes, maybe. Okay, so 0, 0, 0.005, 0, 0, 2, 0. Okay, no, yes, maybe. So if you have zeros that are in between non-zero digits, if you have zeros in between non-zero digits, those are always significant. So yes, they are significant. Zeros on the left are placeholder zeros, and zeros to the right, maybe you have to ask yourself, is there a decimal? And if there is decimal, no. Significant, no. Decimal, yes. Significant, yes. Okay? So in this particular number here, we would have 1, 2, 3, 4, 5 sig figs. Okay? Is that ringing bells? Okay, very good. Numbers like the 1 and the 60 in 1 minute per 60 seconds or 60 seconds per 1 minute, how many sig figs in those? In the 1 and the 60 in 1 minute per 60 seconds, yes? One has infinite sig figs. How about the 60? It also has infinite sig figs, because there's not approximately 60 seconds in a minute. A minute is defined as being 60 seconds. That is the definition of seconds and minutes in relation to one another. So anytime you have a conversion where it is defined 7 days in 1 week, it's not sometimes going to be 8 days in a week, right? It's not going to sometimes be 60.27 seconds in a minute. It is exactly 60 seconds in a minute. So those have infinite sig figs, and so you would not just discount them from your calculations entirely and just be like, I will only look at this one to figure out my sig figs. Okay? All right. You guys are good with converting grams to moles and moles to grams? Yes? Wait, no? Okay, if you have forgotten, again, Hebden Chemistry 11 has practice. Again, I'm not going to spend class time on it other than to say that when you calculate the molar mass, where do you find the molar mass? The molar mass is calculated from values on the periodic table.
Oh, because you just look at the back page. It tells you the.
You get the masses. Okay, so if you look at zinc, it will say at the bottom 65.4. Okay, so on our data booklet, on our periodic table, zinc is 65.4. And if you have trouble finding it on the front, there is also the alphabetical listing where you're like, okay, here's zinc, and it is 65.4. Where did that go? What is the unit of that 65.4? Not just grams, grams per mole. Now you have a conversion factor that allows you to convert between grams and moles, okay? All right, so you could, if you wanted to convert grams into moles, you would put your grams on the bottom to cancel with the grams, and you would have 1 mole on the top. Okay, so you can take your molar mass and turn it upside down if you need to. Like I said, Hebden has a lot of that, and if you're having any trouble with it, come see me at Flex Time. All right, be kind to whoever is reading your work and box your final answer. I'm gonna really encourage that. It makes your life much easier because when you get things back, you don't have me writing, where's your answer? It makes my life easier because I can just look at it and, you know what? If you get the right answer, and maybe you did a little something wrong in your work, I might not notice it even. Sometimes, because sometimes I look and I'm like, oh, that's good, 4 out of 4. And I might even miss something in there. I'm more likely to mark something correct, even if there's something incorrect in there, than I am to mark something wrong if it's actually right. You know what I mean? Like it takes thought to mark something wrong. It takes no thought to be like, oh, that looks good, yay. All right. Okay, so calculations involving rate. Honest to God, we never use 22.4 liters per mole in Chem 12. So I don't even know why I have an example here, but you need to do things like be able to convert between milliliters and liters. Can we all do that, milliliters and liters? Yes? Good. Using rate as a conversion factor. So here's a question where if we have 0.34 grams of magnesium is used per second, that means we know we can write 0.034 grams per second, and that's grams of magnesium per second.
We know the rate there.
Yeah, we're given the rate. That is the rate right there. That is our rate. And this is on page 6, if anyone's gotten lost, because I've sort of skipped through a bunch of stuff. So that is our rate. We want to calculate the number of moles of magnesium used. And we want to calculate the amount used in 6 minutes. So we are starting with 6 minutes. What can we convert minutes into? Minutes can be converted into seconds. And because we have grams per second, we can convert seconds into grams. And because we know the molar mass, we can convert grams into moles. Do we need to take a longer look at that, or are we okay with that? Longer look, anyone? No. All right. Cool. Reaction rate using stoichiometry. How do we feel about stoichiometry? Do we remember what it is? It is using the coefficients. Okay, so you're using the coefficients from the balanced equation. You're converting from substance A to substance B. You're converting from the moles of substance A to the moles of substance B. And in order to do that, you use the mole ratio, which you find from the coefficients of the balanced reaction. So if I give you a rate for a consumption of ethane, and it is consumed at 0.66 moles per second. That is 0.66 moles of C2H6 per second, sorry. And I want the rate of consumption of O2. I can cancel my moles of ethane and find my moles of O2. And where do I get the conversion for that? Well, I have to go back to my balanced equation and say for every 2 moles of ethane, I use 7 moles of O2. Are we good with that? Is that looking familiar? The only thing we've done now that's different from last year is we've put a per second on the bottom, right? And that just carries on across. There's nothing different than last year other than that. All right. You cannot use the coefficients for anything other than mole to mole. You cannot say that we'll convert grams to grams. Do you remember this? Mm. So I could not say, let's say I wanted to take my rate of aluminum per second, that's 67.5 grams of aluminum per second. I could not say that there are, and I wanted to find Br2 in grams per second. I could not say that there are 3 grams of Br2 for every 2 grams of aluminum. That would be bad. No. Okay, you cannot do that. You cannot use those to go from grams to grams. You would need to convert grams of aluminum first into moles of aluminum. Then you could use the 3-to-2 ratio, between bromine and aluminum.
We can't use grams for fluid.
You have to go to moles first to use that mole ratio, okay? You cannot just say, oh, it's a 3-to-2 ratio, and off I go. 67.5 times 3 over 2, all done. No, you would have to convert into moles first. So you would find moles of aluminum, and then you convert that to moles of bromine, and then you convert that to grams of bromine. Okay? So what that looks like is anytime you have anything other than moles, so this could be, for example, you could have grams of A, you could have liters of A, whatever it is, you would need to convert it first to moles of A. Then you would need to convert that into moles of whatever your unknown substance is, substance B, and then you could find grams of B or liters of B or the concentration of B, whatever you need to, but it requires that step in between. Okay, so always go to moles first before you use the coefficients. Alrighty. And let's see. Oh. No, we don't need to do that. Okay. This is just more of how you could measure rate in the lab. So you're going to look at states and you're going to use common sense. So we have a reaction here. We have calcium carbonate solid reacting with hydrochloric acid. And you end up getting H2O plus CO2 gives CaCl2. And this is actually going to come up later in the course. So I'm going to show you how to predict the products of this reaction, because you may or may not know that. You may or may not remember it. Okay? What kind of reaction does this look like? Those are my reactants. What type of reaction? That's a double replacement reaction, okay? So we would just combine our outside ions, CaCl2, yeah? And we would combine our inside ions, H and CO3, so we get H2CO3.
But they always break apart.
But H2 and CO3 always break apart into water and carbon dioxide. And that's just something that you need to know. You should memorize this. So anytime you see H2CO3 as a product, instead of writing H2CO3, you will replace it with carbon dioxide and water. Okay? So take a look at your states here. You've got a solid, you've got aqueous, you've got a liquid, you've got a gas, and you've got aqueous. And I would like you, without looking at the answers, to think of some ways that you could measure rate for that equation.
What is H2O? Water. So I know. Water is a liquid.
Hmm?
No, water is a gas.
Water is a liquid?
Water is a liquid. Yeah.
Yeah. Sorry, what was the question?
No, I mean, like, we can measure like the rate of the reaction of like moisture.
Of water?
Or carbon dioxide, maybe. No, that's like.
Okay, not water, because water is a liquid and it just becomes more water in the aqueous salt, right? There's like water everywhere and now there's just a little bit more water.
Okay.
Yeah? So what do we think about water? Could we measure anything to do with the rate of water?
It's a volume. Except all of that.
So we have here an aqueous system. So what is it full of already? Water. So if we put a little bit of more water in there, are we going to be able to tell the difference? No, it will not make a significant difference to the volume. So water is not a good choice. Okay, so we cannot use water to measure the rate. Has anyone found something that they would like to use to measure the rate? Anyone got one that they would like to share? Don't be shy. I won't bite. Neither will your classmates. They'll be impressed that you were bold enough to say something.
Wait,
They'll be like, I was too shy. That person said something. Wow.
Wait, both of them.
Yes.
With the map, the gas escapes.
Yes, we could measure mass because the gas is escaping. Okay. And that would be the mass of the, what did we call it? That whole thing, that whole reaction vessel with everything in it, that would be the mass of the system. And in order to do that, you would need to have a closed system or an open system. Do we want to have a closed system with a stopper? Or do we want to have an open system with no stopper if we're looking at a change in mass due to a gas escaping? No stopper. So that needs to be an open system. Now, gases are always beautiful. Okay, love that. What else could we measure about the gas? We can measure the pressure of the gas. We can measure the volume of the gas. Would pressure be increasing or decreasing? Pressure would be. So if I measure pressure, what I would have to do is I would have to put a stopper on here and I would have to put a little pressure meter, a barometer. And it's a closed system. So would the pressure be increasing or decreasing as time goes on? We're making more gas. And remember, pressure is how much those particles bash into the sides of the container, how much they bash into the pressure gauge. As we get more and more gas particles, what's going to happen to the gas pressure? It's going to increase because you get more bashing into the sides of the container. Do we have that? There we go. Okay, so we could measure down here. We already had the mass of the system. The mass will decrease as the gas escapes. We could measure a change in pressure over a change in time, and the pressure would increase. As more gas is produced. Did that have to be a closed system or an open system? Closed system. So number one, as CO2 escapes, the mass will decrease. Number two, we've got a change in pressure over change in time. I'm guessing that pressure is probably on the next page. Oh, it's not. That's okay. Okay. What else could we measure here while we're looking at stuff? What else about the gas? We've done mass. We've done pressure.
Volume.
We could do volume, okay? You could do a change in volume of H2 gas over a change in time. Would that be increasing or decreasing as time goes on? The volume of gas. Are you making gas or are you using gas up?
But are we using open systems with?
You would have to, it's a closed system, but it's not closed in terms of its the volume, like it's a changeable volume. But the gas doesn't escape to the outside world.
So it's the same because the volume can only be in the tank.
Do you remember, like, the gas moves into here? Do you remember we talked about that? Yeah. Or we have that syringe and the gas pushes against the syringe, making the volume of gas more. Okay, let's go back and look at that picture. Okay. Okay, here we are. Okay, so here on page 4, we have our reaction. We have our magnesium resin, we have our hydrochloric gas. Bubbles of H2 come up, and as these bubbles of H2 go up, they push this part of the syringe. So this part will end up now over here. So we started having this much gas and we finished having that much gas. So it increases. You cannot make a gas and have a smaller volume of gas, right? You could even just think of, if I put a balloon on the top, right? No fancy equipment, but I've got a balloon on the top of the flask and the gas is coming out. Is that balloon going to get smaller or bigger? Bigger, yeah. Okay, so even without the fancy equipment, you can be like, the volume is going to increase. Okay. So that volume will increase. Now, before we go jumping ahead, I would like to ask, does anybody see anything else in there that would be easy to measure? Maybe I'll get rid of all my things here so you can see it more cleanly. You could do the mass of this CaCO3 as long as you looked at, as long as it was like you got rid of all of it. Like you would have to use it all up. And you'd have to be like, is it there? Is it there? Is it there? It's all gone. You couldn't measure it along the way. Do you know what I mean? Like you couldn't measure it at 5 seconds and then at 10 seconds and then, because it's a powdery kind of a substance and it's going to be wet and it absorbs the water. It's like if you put chalk in water, it just gets wet, right? So you would be measuring the mass of the water. So yes, you could use the mass of CaCO3 as long as you're doing an average rate where it's over the entire time frame to use up all of the CaCO3. So you could do a change in the mass of CaCO3 over a change in time. Will that increase or decrease mass of CaCO3? It's going to increase or decrease as time goes on? Decrease, because it's getting used up. It's a reactant. Okay, good stuff. How are we doing? Would we like to do like a little stretch? No, we're good? Okay, just keep going. All right. So if we were to graph the change in the mass of the system, let's do that. This is the change in mass of the system over time. It might look like this, yes? And you would have time on the x-axis and you would have the mass on the y-axis. And if you calculate your slope, slope is the rise over the run, it is delta y over delta x, which is delta mass over delta time. What would your units there be? Grams per second. Okay, so your unit of your slope would be grams per second. And this particular slope will give you an average rate. So if you did a lab, you could plot your data in the graph, use the slope of the best fit line to find the rate. So the slope is the rate. So anytime you have a graph of a quantity versus time, you can find the rate from the slope. Now, most often, you're not going to get something that looks like this, a nice straight line. Most of the time, you're going to get a graph that looks like this, where a reaction often will start quickly. Okay, when you have a steep slope, that's a fast rate. And when you have a shallow slope, that's a slow rate. And you could find an average rate for this. You could take 2 points on the graph and find the average rate between point A and point B. Okay, you could definitely do that and just pretend it's a straight line for that area. I think, though, on the next page, we actually have some other useful stuff. Let's go take a look. Yeah, okay, so this shows how you could take an average rate. You could say, what is the average rate between 0 and 30 seconds? So the average rate between 0 seconds and 30 seconds. And you would just take the point at 0 seconds and you would take the point on the graph at 30 seconds and you would plug in your grams and your grams. You would plug in your seconds and your seconds, and you would get negative 2.7 grams per second. Are we good with that, or do I need to talk more about how I got those numbers? You guys are good with reading graphs? Okay. Sometimes, however, we don't want the average rate. Sometimes we want an instantaneous rate. Anyone taken physics know the difference between average and instantaneous rates? If you've not done it, don't worry, okay? Basically, what we would have to do, and honestly, we don't spend much time doing this in chemistry at all. I only mention it because you will see it in university, but you won't have to really read graphs and find instantaneous rates in Chem 12. But if I said, what is the instantaneous rate at 22 seconds? I don't know why I'm rewriting it, it's right there. What you would have to do is you would have to draw, if you're doing it by hand, if you're not doing like calculus or something like that, I'm sure if you could do calculus, you could probably just find it. But I don't remember how to do calculus because Chem 12 does not require calculus, nor does AP Chem, so I don't know any calculus anymore. What you do is you draw a tangent line. Now, what the heck is a tangent line? If I were to draw any curve, well, that should not, I need a line, not a highlighter. If I draw any curve, and I say, what is the tangent right here? What I try to do is I try and draw a diagonal line that touches the graph only at that point. So I don't want it to go like this, right? I don't want it to be, that's tilted too far. That's not a tangent line. I want it to go so it just touches the graph right there and then it comes off. That's even not so good. I'm going to make it more obvious. Let's make it a really, really bold curve, okay? The tangent line right there would just touch right there. Does that make sense? And if it doesn't make sense, like I said, we're not doing it really in Chem 12 anyway, so you don't need to worry, okay? But you could draw a tangent line. You would pick 2 points on the tangent line and find the change in mass over the change in time, but we're not going to talk about that because we don't really do it. Homework for that is going to be Hebden page 6, number 3, Hebden page 11, read it and do page 11, numbers 18 and 19, but we're not going to stop because we never stop. Page 6, number 3, read page 11, do numbers 18 to 19. Okay. Whoops, that's not what I wanted to do. Come back. We are now going to be on page 11. Yep. Okay, we have a question here, and you probably have enough tools in your tool belt right now to actually do this question without me telling you how to do it. So what I'm going to ask is that you read this question and that you try to answer it. And remember that rate is equal to the change in amount over the change in time. And there will be some unit conversions in here as well. So you are going to try to find the rate in the volume of H2 produced per second and the moles of zinc produced per minute. Okay. So you just write the equation and fill in the numbers from what you've got there. Okay. If it just says volume, you get to choose. So if you got milliliters in the question, I would go with milliliters, all of milliliters of liters. Oh yeah, I would go with milliliters. Folks, if it doesn't specify whether volume has to be in milliliters or liters, you can use either. So I would use what is ever given in the question.
You know it. From.
Right. Okay, so you want to change the mouth over to the time. So in this case, you want to change the mouth over a change of the time. So let's find the volume of H2. So go on that one. It is indeed. Okay, so we've got that's our volume. And that is our time. So see that? Yeah, cool. Yeah. There are calculators here. Folks, if you need a calculator, there are calculators just here.
That's way too easy.
Super fancy for the boards. By accident. Well, I was using calculators at a rate of 5 or 6 there, and they're like $2 a pop. I buy them myself, so I'm like, I think it's a good board. I know there's pictures where it makes it too, and I'm like, it's not for those shoes. Oh, yeah. You don't get it, okay. So these lines are all. So I'm gonna use mine with all these big. Change the amount divided by the no. So yeah. Because what you've got here is it's tricky because it's yeah. If anyone is stuck, for A, you're going to want rate is equal to the change in volume of H2 over the change in.
But we can leave it in milliliters, right?
You can leave it in milliliters, right? And there are 2 milliliters given here. We are given milliliters of HCl and we're given milliliters of hydrogen gas. So be careful to use the right milliliters. You want to use the milliliters of hydrogen gas. And hopefully the question also gives you a time. Lo and behold, it does. It gives you 2 minutes. And you would be done if it asked for the rate in milliliters per minute, but it asked for it in milliliters per second.
Wait, if we just write 2 minutes without the OO, would it be wrong?
This has 3 sig figs. So your answer should be 3 sig figs. Okay? Yeah.
No, but like wait, I forgot like when do we like how many sig figs for the final answer? It's like when we multiply and subtract like different.
We'll talk about that. Yes. Lowest sig figs, yes. Yeah. And if you're trying to remember your sig fig rules for multiplication and division, you go to the least number of sig figs in the calculation. So you have a 4 sig figs and you have a 3 sig figs. So your answer should have 3 sig figs. When you're adding, you're going to go to the first uncertain digit. We'll talk more about that when we actually add something, okay? So I would then have to round this to 4.12 milliliters per second.
For B, how many sig figs is it for B? Is it also 3?
It's also 3, yeah.
But if we put in scientific notation, do we also have to make it 3?
It's 3, whether it's in regular or scientific notation, yeah.
So if I get like something like
So folks, your homework is going to be covered in page 6, number 3, reading page 11, doing 18 and 19, and I'm going to add in page 15 from your green book.
page 15.
Page 15. That's all going to go up on Teams.
But we do page.
Do page 15.
Do we do anything else? Or?
If you want to, you can do more. But I'm going to say 15. Anytime you want to do more, anytime you have time to do more, it's never a bad thing. But like I said, just like I said, if you have more time, do more. If you have less time, do less, right? And there will be times when I tell you, work your tail off on chemistry this weekend, for example, because you've got X, Y, or Z. Not yet, though. Yes. Can I do B? Yes, we can do B because we have 1 minute left. Okay, so B is going to be rate is equal to, thank you, a change in moles of zinc over a change in time, but I do not have moles of zinc yet. So I am going to, we start with 2.45 grams of zinc and we finish with 1.0 grams of zinc.
Where did we 2.5?
That's what we start with. A student places 2.54 grams of zinc.
With the find a change in things.
You have to find the change in the mass of zinc, turn it into moles.
Oh, I forgot.
Because we only have 1 minute, would you like me to show this to you next day? Okay, cool. Because nobody's paying attention to me right now. Everyone's like, I'm just ready to go. So I will show you how to do to B next day, okay? If you've already done B successfully, that's great. What was the answer? I don't know. It's in the answer key. Yeah?
Wait.
Hi.
Wait. Sorry. So we can use this to find this one. Well, like we can't just plug in 1.1 divided by 2. We have to like subtract this by that.
Oh, no, that's fine. Oh, yeah, no, because that's your final mass. That's not how much was used up.
But how do we know this?
You read the question carefully.
Wait, how do we know like this? For the hydrogen, like how much that is used up?
Because it says it produces that much hydrogen.
So
you need to really get good at reading what the sentence says and interpreting what it means. So you have literally produced exactly that much. Yes? How much have you used up? Nowhere in that question does it say you used 1.01 grams. It says you started with 2.54 or 45 and you finished with 1.01. So you have to calculate how much was used.
okay.
Yes?
Thank you.
Hi.
Shouldn't it be changed in time? So wouldn't it be 0 minus?
Yeah, it would be, but I'm not gonna get too excited about it right now.
Because it's gonna
we
end
ran
up
out
in
of- yeah,
negative.
we ran out
Oh,
of
of course
time.
not. Like, oh, how much is it?
Yeah.
You're
But the answer
absolute-
would be.
You're absolutely, yeah. Or hang on, it would be 2 minutes minus 0. Because final time minus initial time, the final time is 2 minutes. The initial time is 0 seconds. Yes, 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 yes.
I think for test during AP Cal,
Yeah,
I will probably have to skip myself.
totally. Don't mind.
I'll keep reading every now and then.
Yeah.
Because I don't have bother.
Yeah. It's totally fine. All good. All good.
Also, about the student,
Yeah.
when do I come?
I don't know. She's gonna come by tomorrow during flex, I believe.
Okay, I'll be here
If
during.
you'd like to meet her, yeah, that would probably be good. Yeah. Hi. You silly, you should have taken AP chemistry with me last semester, but that's okay.
That's what I told him. He doesn't listen.
Didn't I tell you that last year? I'm like, Tarim, you should take AP chemistry with me. You'd be a good choice. Okay, so what I'm going to do is I'm going to add you to my AP chemistry team. Okay, and that way you'll have, like, I've got review books there. I've got all kinds of stuff. You can learn with, because he's doing the 11 Enrich stuff this year.
I have to do my 11 and Rich. I have to do the.
Jofi as well. Do you know Jofi? Yeah, he's also doing it. So
But
you
you're
can-
doing it together.
yeah.
You're coming with him.